NENOMATICA, where mathematics meets YouTube excellence. Exponential equations. Welcome to this mathematics tutorial. Today, we'll solve a problem involving an exponential equation with a parameter. Our problem asks us to find all values of parameter as such that the exponential equation 4 to the power of x minus a times 2 to the power of x minus a plus 3 equals 0 has at least one solution. To solve this problem, let's start by making a substitution to convert the exponential equation into a quadratic equation. We'll use t equals 2 to the power of x. Now, we need to replace 4 to the power of x in terms of t as well. Since 4 to the power of x equals 2 to the power of 2x, and 2 to the power of x equals t, 4 to the power of x equals t squared. So our equation becomes t squared minus a times t minus a plus 3 equals 0. This is a quadratic equation in terms of t. Now here's the key insight. Since t equals 2 to the power of x, and since 2 to any power is always positive, t must be positive. Therefore, for the original equation to have at least one solution, our quadratic equation must have at least one positive root. For a quadratic equation to have a real solution, its discriminant must be non-negative. The discriminant of our quadratic equation is b squared minus 4ac. In our case, the quadratic is in the form t squared minus a t minus a plus 3 equals 0, which matches the standard form a t squared plus bt plus c, where a equals 1, b equals negative a, and c equals negative a plus 3. So the discriminant is delta equals b squared minus 4ac equals negative a squared minus 4 times 1 times negative a plus 3. This simplifies to a squared minus 4 times 3 minus, which gives us a squared plus 4 a minus 12 greater than or equal to 0. We can factor this quadratic inequality, which gives us a minus 2 times a plus 6 greater than or equal to 0. This inequality is satisfied when either it is less than or equal to negative 6 or it is greater than or equal to 2. However, we need to further analyze these values of a to c, which ones actually give positive solutions for t. For a quadratic equation, t squared minus a t minus a plus 3 equals 0. We know the following about the roots. The product of roots t1 times t2 equals c over which is negative a plus 3. And the sum of roots t1 plus t2 equals negative b over which equals a. Let's consider the two cases we found earlier. First, when it is less than or equal to negative 6. Here, t1 plus t2 equals a, which is negative. Also, t1 times t2 equals 3 minus a, which is positive because it is negative. If the sum is negative and the product is positive, then both roots must be negative. Since t must be positive, and both roots are negative when it is less than or equal to negative 6, the original equation has no solution for these values of a. Now, let's consider the second case, when it is greater than or equal to 2. Here, t1 plus t2 equals a, which is positive. Having a positive sum doesn't guarantee a positive root, but let's check further. When it equals 2, the discriminant is 0, giving exactly one root. This root would be a over 2 equals 1, which is positive. For a greater than 2, the discriminant is positive, giving two distinct roots. Since their sum is positive and their product can be either positive or negative, at least one of the roots must be positive. Therefore, for a greater than or equal to 2, the original exponential equation has at least one solution. So, the values of the parameter are such that the given equation has at least one solution are greater than or equal to 2. We're going to solve a system of exponential equations. Let's see the example. Let's start with the first equation. We have 7 to the power of 2x minus 4 equals 49 to the power of x plus y minus 3. First, let's rewrite 49 as 7 squared. This gives us 7 to the power of 2x minus 4 equals open parenthesis 7 squared close parenthesis to the power of x plus y minus 3. Next, we can use the power rule for exponents. When we have a power raised to another power, we multiply the exponents. This gives us 7 to the power of 2x minus 4 equals 7 to the power of 2 times open parenthesis x plus y minus 3 close parenthesis, which is 2x plus 2, y minus 6. Since both sides of the equation have the same base, 7, the exponents must be equal. So we get 2x minus 4 equals 2x plus 2, y minus 6. Let's simplify. we can subtract 2x from both sides to get negative 4 equals 2y minus 6. Now, let's add 6 to both sides. We get 2y equals negative 4 plus 6. Simplifying, we get 2y equals 2. Dividing both sides by 2, we get y equals 1. Now, let's move to the second equation. We have 8 to the power of x minus y equals 0.25 to the power of y minus 1. First, let's rewrite our bases. We know that 8 equals 2 cubed, and 0.25 equals 25 over 100. Using the power rule, we can rewrite the first part as 2 to the power of 3 times open parenthesis x minus y close parenthesis, which is 2 to the power of 3x minus 3y. For the second part, we can simplify 25 over 100 as 1 over 4. Now, we can rewrite 1 over 4 as 2 to the power of negative 2. Again, using the power rule, this becomes 2 to the power of negative 2 times open parenthesis y minus 1 close parenthesis, which is 2 to the power of negative 2 y plus 2. Since both sides have the same base, 2, the exponents must be equal. So we get 3x minus 3 y equals negative 2y plus 2. Let's add 2y to both sides to get 3x minus 3 y plus 2 y equals 2. Simplifying, we get 3x minus y equals 2. And we already know that y equals 1 from the first equation. Let's substitute y equals 1 into our equation. We get 3x minus 1 equals 2. Adding 1 to both sides, we get 3x equals 2 plus 1. This gives us 3x equals 3. Finally, dividing both sides by 3, we get x equals 1. So our solution is x equals 1 and y equals 1. In today's video, we'll solve a problem involving the number of subsets of sets with different numbers of elements. Here's our example. The number of subsets of a set with 2n plus 3 elements is 32 times the number of subsets of a set with n minus 1 elements. We need to find the value of n. First, let's recall an important fact. The number of subsets of a set with n elements is 2 raised to the power of n. Let's use this fact to set up our equation. The number of subsets of a set with 2n plus 3 elements is 2 raised to the power of 2n plus 3. And this equals 32 times the number of subsets of a set with n minus 1 elements, which is 2 raised to the power of n minus 1. We can simplify this equation by converting 32 to 2 raised to the power of 5, since 2 to the 5th power equals 32. Now, we can use the law of exponents, which states that when multiplying powers with the same base, we add the exponents. So 2 to the 5th power times 2 to the n minus 1 power equals 2 to the power of n plus 4. Since the bases on both sides are the same, specifically 2, the exponents must be equal. Therefore, 2n plus 3 equals n plus 4. Now we solve for n. We subtract n from both sides of the equation to get 2n minus n equals 4 minus 3. Simplifying, we get n equals 1, which is our answer. Let's verify our answer. When n equals 1, a set with 2n plus 3 elements has 2 times 1 plus 3, which is 5 elements. And a set with n minus 1 elements has 1 minus 1, which is 0 elements. A set with 5 elements has 2 to the 5th or 32 subsets. A set with 0 elements has 2 to the 0 power, which is 1 subset, the empty set. And 32 is indeed 32 times 1, confirming that our solution is correct. So the answer to our problem is that n equals 1. In this video, we'll work through a combinatorics problem involving the number of subsets of a set. Let's begin. Let's examine the following example. The number of subsets of a set with n plus 1 elements is 28 more than the number of subsets of a set with n minus 2 elements. Find the natural number, n. Before we dive into solving this problem, let's quickly recall what we know about subsets. For a set with n elements, the total number of possible subsets is 2 to the power of n. This includes the empty set and the set itself. Now, let's use this formula to set up our equation. For a set with n plus 1 elements, the number of subsets is 2 to the power of n plus 1. For a set with n minus 2 elements, the number of subsets is 2 to the power of n minus 2. Let's rearrange this equation. We'll move 2 to the power of n minus 2 to the left side of the equation. Now, let's rewrite these exponential terms using the laws of exponents. 2 to the power of n plus 1 can be written as 2 to the power of n times 2 to the power of 1. Similarly, 2 to the power of n minus 2 can be written as 2 to the power of n times 2 to the power of minus 2. Since we have 2 to the power of n in both terms, let's factor it out. We get 2 to the power of n times the expression in parentheses, 2 minus 1 over 4. Let's simplify the expression inside the parentheses. 2 minus 1 quarter equals 7 quarters, or 7 over 4. Now, let's solve for 2 to the power of n. We'll divide both sides by 7 over 4. This gives us 2 to the power of n equals 28 times 4 over 7. Let's simplify the right side. 28 times 4 equals 112, and 112 divided by 7 equals 16. Since we have 2 to the power of n equals 16, and 16 is 2 to the power of 4, we can write 2 to the power of n equals 2 to the power of 4. When we have the same base on both sides of an equation, the exponents must be equal. Therefore, n equals 4. Let's verify our answer. With n equals 4, a set with n plus 1 elements or 5 elements has 2 to the power of 5 or 32 subsets. A set with n minus 2 elements or 2 elements has 2 to the power of 2 or 4 subsets. And indeed, 32 minus 4 equals 28, which matches our problem statement. Therefore, n equals 4 is correct. In this problem, we used our knowledge of the number of subsets, formula, and laws of exponents to solve for n. The key insight was recognizing that for a set with n elements, the number of subsets is 2 to the power of n. Thanks for watching. In this video, we'll solve a problem about the number of subsets of a set. Let's recall an important fact. The number of subsets of a set with n elements is 2 raised to the power of n. Now, let's set up our equation. According to the problem, the number of subsets of a set with k plus 3 elements is 2 raised to the power of k plus 3. This equals the number of subsets of a set with k elements, which is 2 raised to the power of k, plus 112. Let's use the properties of exponents. We can rewrite 2 raised to the power of k plus 3 as 2 raised to the power of k times 2 raised to the power of 3. We know that 2 raised to the power of 3 equals 8, so we have 2 raised to the power of k times 8 equals 2 raised to the power of k plus 112. We can factor out 2 raised to the power of k on the left side, getting 2 raised to the power of k times the quantity 8 minus 1, which equals 112. Simplifying 8 minus 1, we get 7. So the equation becomes 2 raised to the power of k times 7 equals 112. Now we can solve for 2 raised to the power of k by dividing both sides by 7. So 2 raised to the power of k equals 112 divided by 7. When we calculate 112 divided by 7, we get 16. So 2 raised to the power of k equals 16. Now we need to find k. Since 2 raised to the power of k equals 16, we can write 16 as a power of 2, which is 2 raised to the power of 4. Therefore, k equals 4. Therefore, k equals 4. In this video, we'll solve a problem about the number of subsets of sets with different elements. Example, the sum of the number of subsets of 3 sets with k minus 2, k, and k plus 1 elements is 104. What is the number of subsets of each set? Let's start by writing the equation that represents our problem. The number of subsets of a set with n elements is 2 to the power of n. So we have 2 to the power of k minus 2 plus 2 to the power of k plus 2 to the power of k plus 1 equals 104. Now, let's express all terms using 2 to the power of k. We can write 2 to the power of k minus 2 as 2 to the power of k times 2 to the power of negative 2. We keep 2 to the power of k as is, and 2 to the power of k plus 1 can be written as 2 to the power of k times 2 to the power of 1. We can factor out 2 to the power of k from all 3 terms. This gives us 2 to the power of k times the quantity. 1/4 plus 1 plus 2 equals 104. Let's simplify what's inside the parentheses. 1/4 plus 1 plus 2 equals 1/4 plus 3, which is 13 over 4. Now we can solve for 2 to the power of k by dividing both sides by 13 over 4. This is equivalent to multiplying by 4 over 13. Let's calculate this. 104 times 4 is 416, and 416 divided by 13 is 32. So 2 to the power of k equals 32. Since 2 to the power of k equals 32, and 32 equals 2 to the power of 5, we can write 2 to the power of k equals 2 to the power of 5. By comparing the exponents, we can conclude that k equals 5. Now that we know k equals 5, we can find the number of subsets for each set. For the set with k minus 2 elements, which is 5 minus 2 or 3 elements, the number of subsets is 2 to the power of 3, which equals 8. For the set with k elements, which is 5 elements, the number of subsets is 2 to the power of 5, which equals 32. And for the set with k plus 1 elements, which is 5 plus 1 or 6 elements, the number of subsets is 2 to the power of 6, which equals 64. Therefore, the sets have 8, 32, and 64 subsets, respectively. Indeed, we can verify that their sum is 8 plus 32 plus 64, which equals 104, confirming our solution. In this video, we will solve a combinatorics problem involving subsets. Here's our example. The number of subsets of a set with k minus 1 elements is 48 more than the number of subsets of a set with k minus 3 elements. We need to find the natural number k. Let's start by setting up an equation. We know that the number of subsets of a set with n elements is 2 to the power of n. So, the number of subsets of a set with k minus 1 elements is 2 to the power of k minus 1. And the number of subsets of a set with k minus 3 elements is 2 to the power of k minus 3. Now, let's move the 2 to the power of k minus 3 term to the left side of the equation. Next, we'll rewrite each term using the laws of exponents. 2 to the power of k minus 1 can be written as 2 to the power of k times 2 to the power of negative 1. Similarly, 2 to the power of k minus 3 can be written as 2 to the power of k times 2 to the power of negative 3. Now, we can factor out 2 to the power of k from both terms. Let's simplify the expression inside the parentheses. 1 over 2 minus 1 over 8 equals 4 over 8 minus 1 over 8, which is 3 over 8. To isolate 2 to the power of k, we multiply both sides of the equation by 8 over 3. Let's simplify the right side. 8 times 48 equals 8 times 3 times 16, which is 384. Now we can divide both sides by 3, and we get 2 to the power of k equals 8 times 16 divided by 3. 8 times 16 is 128, so 2 to the power of k equals 128, which we can write as 2 to the power of 3 times 2 to the power of 4. Using the laws of exponents, we can add the exponents when multiplying powers with the same base. So, 2 to the power of 3 times 2 to the power of 4 equals 2 to the power of 3 plus 4, which is 2 to the power of 7. Since the left side is 2 to the power of k, and the right side is 2 to the power of 7, we can conclude that k equals 7. This is our final answer. Let's verify our solution. With k equal to 7, a set with k minus 1, or 6, elements has 2 to the power of 6, which is 64, subsets. A set with k minus 3, or 4, elements has 2 to the power of 4, which is 16, subsets. The difference is 64 minus 16, which equals 48, confirming our answer. To summarize, we solved this problem by, first, setting up an equation using the fact that a set with n elements has 2 to the power of n subsets. Then, we performed algebraic manipulations to isolate 2 to the power of k. Finally, we determined that k equals 7. Welcome to today's math lesson. Today, we're going to solve a problem about the number of subsets in sets. Here's our problem. The number of subsets of a set with 5k minus 1 elements equals the product of the number of subsets of two sets, one with k plus 5 elements, and another with 3k minus 2 elements. Find the value of k. Before we solve this problem, let's recall some important facts about sets and subsets. For a set with n elements, the number of possible subsets is 2 raised to the power of n. This is because for each element, we have two choices, either included in the subset or excluded. Now, let's use this knowledge to set up our equation. For a set with 5k minus 1 elements, the number of subsets is 2 raised to the power of 5k minus 1. For a set with k plus 5 elements, the number of subsets is 2 raised to the power of k plus 5. For a set with 3k minus 2 elements, the number of subsets is 2 raised to the power of 3k minus 2. According to our problem, the number of subsets of the first set equals the product of the number of subsets of the other two sets. Let's simplify the right side of our equation. When we multiply exponential terms with the same base, we add the exponents. So 2 raised to the power of k plus 5 times 2 raised to the power of 3k minus 2 equals 2 raised to the power of the sum of the exponents, k plus 5 plus 3k minus 2. This simplifies to 2 raised to the power of 4k plus 3. Now, for this equation to be true, the exponents on both sides must be equal. This is because if a equals b, then 2 raised to the power of a equals 2 raised to the power of b. If and only if it equals b. So we have 5k minus 1 equals 4k plus 3. Let's solve for k. First, we'll subtract 4k from both sides. 5k minus 1 minus 4k equals 4k plus 3 minus 4k. This simplifies to k minus 1 equals 3. Adding 1 to both sides, we get k equals 4. Let's verify our answer by substituting k equals 4 back into the original equation. For the left side, we have 2 raised to the power of 5 times 4 minus 1, which is 2 raised to the power of 19. For the right side, we have 2 raised to the power of 4 plus 5 times 2 raised to the power of 3 times 4 minus 2, which is 2 raised to the power of 9 times 2 raised to the power of 10, which equals 2 raised to the power of 19. Both sides equal 2 raised to the power of 19, confirming that k equals 4 is our solution. In summary, we solved this problem by, first, recalling that a set with n elements has 2 raised to the power of n subsets. Next, setting up our equation based on the problem statement. Then, simplifying the exponential expressions and solving for k. Finally, verifying our answer by substituting back into the original equation. The value of k is 4. Example. Let's solve the following exponential equation. First, let's rewrite the square root of 2 as 2 to the power of 1/2. Now, we'll apply the power of a power rule, which states that when a base with an exponent is raised to another power, we multiply the exponents. So we multiply 1/2 by negative square root of 2. When we have a negative exponent, we can rewrite it as a reciprocal with a positive exponent. So 2 to the power of negative square root of 2 over 2 becomes 1 over 2 to the power of square root of 2 over 2. Now, let's rewrite the exponent. We can express square root of 2 over 2 as 1 over square root of 2. Next, we can rewrite 1 over square root of 2 as the square root of 1 over 2. And the square root of 1 over 2 can be written as 1 over 2 to the power of 1/2. Looking at our equation, we notice that x raised to the power of x to the x equals 1 over 2 raised to the power of 1 over 2 to the power of 1/2. For this equation to be true, we need x to equal 1 over 2 and x to the power of x to equal 1 over 2 to the power of 1/2. In this video, we'll solve an exponential equation and find the sum of digits of a specific value related to our solution. Let's look at our example. We know this equation has only one real solution. We need to find the value of x, and then calculate the sum of digits of 100 divided by x. Let's begin by simplifying the exponent on the right side of the equation. We can rewrite negative 3 plus 1.5x as negative 1.5 times open parenthesis 2 minus x close parenthesis. This helps us connect the exponent to our variable on the left side. Now we'll take advantage of the form of our equation. We notice that the left side has the term 1 over 2 minus x. Let's raise both sides to the power of 1 over 2 minus x. On the left side, this gives us 1 over 2 minus x squared. On the right side, we apply the exponent to our expression. Using the properties of exponents, we can simplify the right side. When we raise a power to another power, we multiply the exponents. So we get negative 1.5 times open parenthesis 2 minus x close parenthesis times 1 over 2 minus x. The factors 2 minus x cancel out in the multiplication, leaving us with negative 1.5. Let's rewrite our equation. The left side becomes 1 over 2 minus x to the power of 1 over 2 minus x. The right side is 2/3 to the power of negative 1.5. We can rewrite this as 3/2 to the power of 1.5. Now we're going to use an important property. When two expressions raised to the same base are equal, their bases must be equal. In our case, this means that 1 over 2 minus x must equal 3/2. Now let's solve for x. We can cross multiply to get 2 minus x equals 2/3, or equivalently, 6 minus 3x equals 2. Subtracting 6 from both sides and dividing by -3, we get x equals 4/3. Now, we need to find 100 divided by x. Substituting x equals 4/3, we get 100 divided by 4/3. This is equal to 100 times 3/4, which works out to 300 over 4, or 75. Finally, we need to find the sum of the digits of 75. That's 7 plus 5, which equals 12. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.